Welcome to the series of videos on the ARM64 assembly language. ARM64 is the processor being adopted by Apple for its current Mac devices. It's also been used in some of the Windows-based systems. And of course, it's the basis for the Raspberry Pi systems. The Raspberry Pi models 4 and 5 are well suited to this series. So in this session, which is part 1, we will be laying the groundwork foundations. And this will prepare us for dealing with some of the more advanced topics in the later videos. The first thing we will examine is the layout of the ARM64 register set. This is the primary way that we will communicate with the ARM64 system. We can generically refer to these registers as RD for the destination register, RN for the first source register, and RM for the second source register. There are a total of 31 general-purpose registers, and we number these as 0 to 30. They can be used in 32-bit or 64-bit mode. If we refer them as 32-bit registers, then we use a W prefix. So in other words, W0, W1, W2, etc. Or if we refer them with the X prefix, then that's 64-bit. So X0, X1, X2, etc. So these registers will be designated as WN or XN. As mentioned, we can also use generic references like RD, which means that we're just talking about a destination register. We are not going to specify whether it's a 32 or 64-bit register. When we deal with 32-bit registers, these are actually the lower half of the corresponding 64-bit X register. So it's the same register, except that we use only the lower 32 bits. If we're reading from the 32 bits of a W register, then the upper 32 bits of the X register are not involved. But when we write to it, then the higher the 32 bits of the register are set to 0. Some other special cases. Register X30 is known as the link register, or the LR register, and this holds the return address for the function. So we should be careful about using this if we're going to be using branches and jumps, which we'll talk about later on. The 0 register is X31 and W31, and will return 0 when read. Write operations will not change the value since it's a read-only register. The program counter keeps track of the program execution, and we will not use it as a general-purpose register. So here the registers, the 64-bit variant is here with the X0, and half the size of that is W0. So this would be the first register X0. This would be the second register X1, X2, and so on all the way up. There are more registers used for floating point, and these are 128 bits wide. But like the previous registers, we can divide them up into smaller quantities. So the Q registers or the quad registers are the full 128 bits. The D registers or the double word registers are 64 bits. The single word registers are 32 bits. Half word are the H registers, and then the byte registers are B. So this is how it works. This is vector register 0, this is vector register 1, and these are the different ones. And towards the end of the series of videos, we're going to talk about the vector functions as well. There's some additional registers we need to talk about and be aware of. So there is a set of bits collectively known as the processor or P state. This is not actually a status register, as found in ARM32 and other systems, but it does hold values for the condition flags. It has a lot more information, but initially, we're going to be mainly concerned with the condition code flags, and these are -0, the carry, and the overflow bits. They occupy the positions 31 to 28 respectively. So when we perform arithmetic calculations, we sometimes need to be aware of these registers to see if we had any overflow or any of those other conditions. There are some other registers as well for exception masking, and these are known as DAIF. So DAIF stands for debug asynchronous, IRQ, and FIQ as fast interrupt requests. We probably won't deal with these in very much detail during this course. If we look at the instruction length on the ARM64, they're actually 32 bits wide. So, again, when we're dealing with either 32-bit registers or 64-bit registers, the instructions themselves tell the ARM process or what to do and are both 32 bits wide. We break these instructions into different bit fields. So we have operation codes, we have immediate fields, we have destination registers and source operands. And the format of these fields will change depending on the type of instruction that we're using. In this case, we're using the move wide with 0 instruction. And here we have 2 bits HW, which signify how much of a shift that we want to do. So we'll look at the move 0 instruction in a little bit more detail later on. In general though, if we look at the instruction format, an instruction could contain the destination register, the opcode, a first source register, and possibly a second source register, or it could be an immediate value, which is a literal value or constant. Again, we're going to show examples of that as well. When we say R like this, we're using the generic terms, so it could be an X register or W register. We're going to use a utility called object dump, and we'll talk about that in more detail later. But object dump will lay the instructions out in this format. So it'll show the address where the instruction resides. It'll show the actual instruction itself, and this is given in hexadecimal. And then it will show the mnemonics of the ARM64 instruction. In this example, we have move into the destination, register X3, this value shown here. This is an immediate value, or we could decide to move the contents of X3 into X4, and this is a register value. The next time we hit an instruction, then it'll be incremented by 4, because the 32 bits are 4 bytes, and then it'll go on right up, and so on all the way through to the end of the program. Now, one of the things we talked about previously, we saw that there were 16 bits for the immediate value. But if we want to fully load a 32-bit register or even a 64-bit X register, how can we do that? Well, we're going to have to do it in stages. So here we'd like to load up the value hex 1, 2, 3, 4, 5, 6, 7, 8. But the most we can do is 16 bits at a time. First, we would have to load this part and then the second part. But then that would overwrite the other one. So how does this work? Well, the idea is that we use the move keep instruction. When we move in the new values, we preserve the old values. We'll load up the first values into the bottom part of the register, and then we'll do a shift operation to move higher up into the register, and we'll load the bits into those upper bit positions. So we could first load the 16 bits into the lower part of the register, and then we would perform a shift of 16 places to get into the higher part of the W register. Or we may have to do 2 more shifts if we wanted to fully load up a 64-bit register. There is a 2-bit field designated HW, which specifies the shift amount to be moved. The table there shows what happens in the first instruction. We load in the value 5, 6, 7, 8, but we do not use a shift. The second instruction loads in the value 1, 2, 3, 4, but we've actually shifted over 16 places to the left. And that's how we fully load 32 bits into the register. Now, with RISC assembly programming, there is a concept of aliases. And because instructions are limited, since we don't have that many bits to play with, instead of just using a myriad of different instructions, we can make certain instructions emulate the others, and they can make life a lot easier as well for the programmer. So an example would be to compare an instruction. This is actually an alias to the subtraction instruction. So what it does is to subtract an immediate value from a register, And then depending on the result of that, such as equal to or less than, etc., it will perform a branch operation. And this is how it works as a compare instruction. Comparisons and branching are covered in a later tutorial. The programmer doesn't have to worry about writing out the complexity of this. Pseudo instructions or aliases can be used instead, which makes life a lot easier for us when coding. So let's get our hands dirty right away by writing a very simple program. So use your favorite editor, whether it's Nano or VI, to generate this program. So we're going to name it Move Registers, and we'll have an extension of .s standing for the source code in assembly. We start it off with .global_start directive, and then we have a label called _start. And this is basically just showing where the program is going to begin. The text section is where we have the instructions. So the instructions here are simply move this value for FF into register X3. So let's use the move immediate operation. Then we do a move register operation. We take the contents of X3 and we put it into X4. So at this point, both of these registers should have the same value. Finally, we do the system call instruction by moving the value 93 into the register W8. Now, what the system call does is to ask the operating system to execute functions on our behalf. In this case, it is the exit system call. We will encounter other system calls as we progress through the sessions. After we've loaded up with the exit system call number, we then execute the call with the service 0 instruction. Before we can run the code, we have to assemble it. So the instruction to assemble is is-o. This generates an object file, which is the binary code. So is-moveregisters.o, that's the object binary. And then we have to give it the name of the source file, which is moveregisters.c. So we're assembling the source file into an object file. The next step is to link and create the executable file. So we do LD for the link editor. The output is going to be a file called moveregisters, and we're going to link in the object file moveregisters.o. And you could have multiple object files if you wanted to generate a single executable file. And then finally we make the code executable. So you may need to change the permissions, and you can do this by simply doing chmod 777, followed by the name of the executable file. And then we run the code with ./moveregisters. Now the program runs, but we don't really see anything. There's not much in the way of validation. So really, without getting into how to print output to the screen, which we will cover later on, we can use the debugging tool to follow or trace the program as it goes along. We're going to use this debugging tool called GDB, and this will allow us to show exactly what's happening, because we can execute the code one step at a time rather than run the complete code at once. So the way we need to enable this is we recreate the object code, but this time we add this -g switch, which generates debug information. So the assemble command is as-g-o moveregisters.o moveregisters.s. The same as before, except we've added the -g, and then we can use the link editor again. We run the debugger by entering GDB with the name of the executable, which here is moveregisters, and then this will invoke the GDB program. We will show a few basic commands here. If you want to list the code, we can do Enter L, and then this will list the source code. Then we can set a breakpoint. So we don't want to execute the code to completion at this point. We want to stop it and run it one step at a time. We enter B1, which sets a breakpoint at the first line of code. And then we run the code so it stops at the breakpoint. Now we can look at the register's content. We can use the command I for info, R for registers, and then it print all the registers out. So nothing has happened at this point. All the registers are showing 0. So if we hit S for step to move into the next line of code, then we're going to load the X3 register with the value FFFF, and we can look at that by showing only that register. We enter IRX3. We'll see the value FFFF is now in there. After we hit the step command to move the contents of X3 into register X4, then we'll see that it also has FFFF. So now we can look at both values. They have the same content, and then we can exit using our system call. So GDB has shown us what's going on, and this is useful, not just in debugging, but also telling us how the program flows, and it helps us to understand things as well. The source layout shows the original source code that was entered prior to assembly. The next layout shows the general purpose registers at the top of the screens. Another useful layout is ASM, which shows the disassembled instructions, and it can be instructive to compare the generated disassembly with the original source code. Previous and subsequent window panes can be selected with the commands layout previous and layout next. The text user interface can be disabled by the command TUI disable and re-enabled with TUI enable. Rather than entering the commands each time you invoke GDB, you can set up default window panes. Go into your home directory and enter the commands listed into a file called .gdbinit. So this is a hidden file. Make sure you use the dot prefix in front of the file name. So you can either use this default script or you can set up your own one depending on your preferences. There are a number of enhancements that build on GDB. We've already seen GDB using the text user interface. There's another useful tool called GDB GUI, and this uses a browser to display information. The instructions for installing this tool are found at the website www.edbgui. After installation, start GDB GUI by entering the following command GDB GUI, with the argument which is the file name. So make sure you specify the complete file name along with the path. The screenshot that we're going to show displays a program that's running through execution. Use the regular GDB commands such as breakpoint run and step. As well as showing the source listing window, you can expand the registers tab, the memory locations tab, and a number of other drop-downs such as the local variables and breakpoints. The memory locations are very useful. We can decide how to show the memory and how many bytes to show at a time. GDB GUI is a great tool, especially if you have the screen real estate to use it to its full potential. Another alternative is GDB Frontend, and again, that can be installed from the website listed above. It's reasonably customizable, but again, it has plenty of places where you can see all the different values such as the variables and registers. You can look at the source code and disassembly. The next program will show how to output text to the screen. To do this, we're going to use a system call again, but this time the call will be write, and it has the value 64 decimal. For this to succeed, we need to load some registers first, and the registers are X0, X1, and X2. X0 will point to the output device, which is standard output, corresponding to the screen, and it'll have the value 1. X1 will be loaded with the address of memory, where our text string is located, and X2 will hold the length of the text string. The steps are load memory with the string. We then have to prime those X registers. And finally, we have to execute the system call. After execution, the string hello will be shown on the screen. Now let's analyze our program using GDB. So, set up our breakpoint as normal. Hit run. Now you may recall that we put the address of this location result into x1. We can look at x1 here and we'll be able to see what its value is. Or we can do this command, info variables. And this tells us that the memory location for result starts at hex 4100E0. So if we hit a few commands here, you'll see after this that the address has been reflected here in x1. So let's have a look at our memory at that location. So we can do x/ and then we do the number of characters or variables or whatever we want to look at with the number. So in this case, we've got 6 characters. Well, let's first of all look at them in hex format. So we can do x/6 x4100E0. Now we can see the characters here, but really that doesn't tell us very much. So we can make this a little bit more friendly for us. So if we do x/6, this time we're going to use B for bytes, and we'll put in the same address, 4100 E0. Now we can see the individual bytes, and there's the 6 of them. This last one, A, corresponds to enter or new line, but you really need to have your ASCII code card to decipher this. So, again, we can make things a little bit easier. x/6, and this time we're going to use C for characters. Now we can see the ASCII values, and there's the characters H through O, followed by the new line character. If we know we're dealing with strings, we can do x/s 4100E0. And there's the whole string complete with the new line. Now here we put in an absolute address, but it's also possible to do something like this, x/s. We can use the ampersand character, and we can put in the variable results, the name of our memory location. So this will give us the address. So instead of using the address, we could just specify the variable name. You can also refer to the register itself. Next, we're going to look at load and store instructions. These are key, and very few programs would execute without using either of these instructions, or most commonly both. So first of all, with the load instruction, the direction is with respect to a register, so the operation is reading from the memory and loading into a register. Data is stored in little endian format, so this is how the least significant byte in a multiple byte stream would be stored into the lowest address location in memory. So if you had a word of 4 bytes, then the lowest byte would be put into the lowest area of memory. With single bytes, it doesn't matter. It will be put into the next location specified. Some of the other processors will use big endian, such as the Motorola 68 series. In fact, ARM64 can use both formats, but will be dealing with little endian. So here's an example. We have 4 memory addresses, 1000, 1001, 1002, 1003. We'd like to store the data hex 012345667. So this byte here is the least significant byte, and it is placed into the lowest part of memory, 1000. The next byte will go into the second location, and so on. Later on, we will discuss memory alignment boundaries. With big endian processing, we have the reverse order. So here's a couple of examples. Let's say we had a symbolic name of my data as a memory location, and this could be reconciled to the address hex for 100110. So the contents of this location, 0x450012FA, that's showing, has the data laid down as 32-bit or word format. But just to show you on the right-hand side, the table shows the individual bytes. Now, if we look at the memory address 41000110, it has the data FA in it. The next location has 12, so you can see here that the most significant is stored here, the least significant is here. So that's the way everything is laid out. With store instructions, the direction is opposite. So we're storing from a register into the memory. Now, when we do loads and stores, we can specify different data sizes. So we'll look at some basic store instructions here. So first of all, we can store data from a register, and the XT there just means any X register. So we store into the memory the register's data, and that'll be a 64-bit store with 8 bytes. Then if we specify WT, then we're going to perform a 32-bit store of 4 bytes. We can do a half-word store with strhwt into the W register, and we can do a byte store with B. In general, the loads and stores have corresponding instructions. And as we progress through our programming journey, this will start to become second nature. The way that we access memory can be different depending on what our ultimate aim is. We refer to these different ways of accessing memory as the addressing modes. And there are several of them on ARM64. We're going to look at the major ones, which are base addressing with an offset, and the offset can be an immediate value or stored within another register. The addressing modes used with the load instruction will involve 2 registers, a source and a destination. The source is the base register, and the destination is the first register specified in the load instruction. The next 2 modes that we will examine are pre-indexed and post-indexed addressing. With pre-indexed, the first action is to increment the base register to point to the next address location, and then we fetch the data at this new address that's being pointed to and load it into the destination register. With post-indexed, we will access the data pointed to by the base register first. We will read this memory location, loading the contents into the destination register, and afterwards increment the base register. So the order in which we increment the registers is different for pre- and post-indexing. The program opposite will demonstrate these modes. The register we're going to use here is X6, the base register. The square brackets represent indirection or dereferencing, and it signifies that the register inside the brackets holds an address. Now let's have a look at that program. Set up a breakpoint as usual and run the programs. First, we're going to initialize a number of registers. Even though they're already at 0, it's good practice to initialize them because they could hold random values, so it's good to know what's going on. The only one that's different here is register X1. We're going to initialize that with a value of 4, and that's because we're going to use this register as an offset when we look at the register offset addressing mode. So hit next until all the registers have been set up with known values. The next line of code loads register X6 with the memory location named dataset1. This line with LDR followed by the equal sign is actually another addressing mode. It's known as PC relative, and we've left this out for the moment, but we will talk about it right after this program, because it really deserves a discussion on its own. So after we've loaded this X6 register, it'll point to the memory where dataset1 was allocated. Now if we look at X6, you can see it has the value hex 4100F0. Now we're going to load register X2 with the values pointed to by register X6, and because these are 64-bit values, we're going to have to load two 32-bit words. So this will be the first and the second words that we defined in dataset 1. So hit Next. And what you have here is the first word that we defined. So this goes into the lower 32 bits, and this is the second word that was defined, which goes into the upper 32 bits. Register X2 now holds the first two words of the contents of the memory location defined as dataset 1. Register X6 points to where the data is stored. This mode is simple base addressing. The next addressing mode is going to employ an offset. So if we set the value to be 4, then we're going to be picking up the second and third words of the dataset. So let's hit Next. And you can see here that we have indeed loaded these values into register X2. So we've added that 4 to the address, hex 4100F0, and now we are pointing to memory location, hex 4100F4, and we will load register X2 with the second and third words that we defined in dataset 1. This is base addressing mode using an immediate offset. Next, if we use register X1 as our offset, instead of an immediate value, then it's going to be the same thing because we previously loaded register X1 with the value 4. So coincidentally enough, X2 is going to hold the same result. So hit Next, and you can see the X2 is exactly the same. This is base addressing mode with a register offset. Now with the pre-indexed mode, this instruction will increment the X6 register by 8. And then we're going to take these values at that new memory location, which is 8 places further on at hex 41F8, and put them into register X2. So we'll hit Next. You can see that this register X6 now points to the new address, and will therefore load the third and fourth words that we defined in dataset 1. Now with the post-index mode, we take the values currently pointed to by X6, load them into X2, and only then do we increment the X register. So effectively, because we're taking the values currently pointed to by X6, then X6 is not going to change its value until after we fetch these current values. And these new values are exactly the same as before. So if you look at X2, it won't change. Hit Next. Now you can see that X6 has been incremented by a further 8 positions. So now it holds hex 41001000. If we look at the memory locations using x/4xw, ampersand dataset 1, you can see this is the first word, second word, third word, and fourth word. So the last thing we did, you might remember, was to have bumped this up by 8. So we had to load in these two values here. So the fourth word goes in the most significant 32 bits, and the third word goes in the least significant 32 bits of our destination. So that's our basic addressing modes program. And in Next, we're going to examine PC relative addressing. So if you look at the instruction LDR load x6 equals dataset 1, our question is, how do we get the memory location dataset 1 into x6? Well, it's done by PC relative addressing. Now, if we disassemble this instruction in object dump, then we can see a number of the fields here. So, the first one that should be recognizable is the X register, X6. So that's in this field. There's an immediate field of 19 bits. So this is how far we want to make our offset. So it's relative to the program counter. This is just the bits to say whether it's a 64-bit or 32-bit instruction. And we have some fixed values for the opcodes here. So basically, these fixed bits signify that it's literal. And it calculates the address by adding this immediate offset to the program counter. The program counter is implicit, so the only register that we are talking about here is destination register. So we're going to use the program counter, but that's explicit with this instruction because we do not manipulate it directly. So there is a limit to this. There are some other tricks we can do, but effectively, you've only got 19 bits, so we are limited to these 19 bits here as well. We have seen that with PC relative addressing, we are somewhat limited since we have less than 32 bits available in the immediate field. There is another method where we can address pages. Pages are 4 kilobytes in size, and because they're larger, we can specify a greater range with a smaller set of bits. Now, the downside is that you have to use a second instruction. So effectively, we specify an immediate value with an instruction called ADRP, and this gets us to a particular page or a specific 4 KB region within memory. And then when we've derived the page, we need to specify a location or an offset within the page that we've addressed. So we need the second instruction for that, which is add immediate. The ADRP instruction selects the page, and then we use the add instruction to generate an offset within that page. The listing shows these two instructions. Many users will not need to address this larger range, but it is important to understand the mechanism if performing tasks such as reverse engineering from C code. Now, if we disassemble the previous listing, you can see as part of the ADRPX1 instruction this value 410000, and then we get information stating _start plus hex FF50. We will discuss this latter part shortly. The program counter's value at _start is hex 4000B0. The ADRP instruction will take the current program counter value and it'll clear the lower 12 bits by ANDing them with the bottom 12 bits of the AND mask set to 0. Note the next video will cover logic instructions. And this will get the alignment to be on the 12-bit 4 KB page boundary, seeing as we've zeroed out those 12 bits and now have the value hex 400000. Looking at the bit field breakdown bits 23 through 5. These 19 bits represent the high part of the immediate bits. Bits 30 through 29 represent the low part of the immediate bits. Combining both fields gives an immediate value of 10000 binary or 10 hex. This 21-bit value is shifted 12 places to the left, giving a result of 100000. The shifted value then is added to the 4 KB aligned program counter value that we previously set in X1, giving a result of hex 410000. And this is what the disassembly instruction ADRPX1 hex 410000 showed. This is the actual 4 KB page that has been selected. The add immediate instruction is used to generate an offset within the page. It disassembles to add x1 hex D4. Now x1 holds the page number, and adding the immediate value of D4 to x1, placing the result in x1, gives a final location of hex 4100 D4. We mentioned earlier that the instruction ADRP showed _start plus hex FF50, which explained hex 410000. If we now add FF50 to the program counter's value at _start, which is shown in the disassembler program as 4000B0, we do indeed get the value 410000. The notation :LO : is an assembler modifier that takes out the lower 12 bits of the symbol message, which equates in the disassembler to hex D4. You note that the symbol message in the original source code has been replaced by a hex value. Next, we want to look at the different variants of the store instruction. We're going to actually look at the memory locations, and we'll see how it changes as we store different amounts of data. We're going to first store a very small amount, namely a byte, then we're going to follow with a half word, and then we'll do 32 bits, 64 bits right up to 128 bits. We're also going to introduce a new instruction load pair, which loads a pair of registers. You can see that at LDPX2X3. We're also going to then manage to store the 128 bits with the complementary store pair instruction x2, x3. So the best way to do this is to illustrate it using GDB. So let's get started. Now we're going to look at the various data sizes that can be used with the store instruction. We're going to store just a single byte, then a half word, and after that words and double words. One of the very useful commands we can use in GDB is this command display, /16xb, the contents of the location output store. This command will continuously show 16 bytes in the memory location output store. The command will express them in hex format, showing a single byte at a time after each GDB command with no additional user input. So let's hit enter. And it shows us that there's nothing in those locations. Set up our breakpoint as normal. Run the command. And we'll issue S to step into the program code. So we've loaded up register X0 with the address of the location where we hold our input data. And again, there's still nothing in output store. We're going to load X1 with the address location of output store. And then we're going to store a single byte into the output store location, which as you've seen is pointed to by register X1. Now observe that we have the value hex 91 stored, which is the first byte of the data from input data. Hit S for the next one. Now we're going to store a half word. So this time it's going to be a store of 2 bytes or a half word. Now we show 9170 in output store. And then we're going to use the regular store instruction with no data size specified. And you can see I'm using it twice, but the key point is when the instruction with no different data size specified is that we're using the W register here in the first case and we're using the X register here in the second case. So what will happen is that this will treat this as a 32-bit word because we're using the W register, and then it'll be treated as a 64-bit word because we specified the X register. Hit step. Now you can see that we've got our complete 32-bit word located in the output store. And we'll hit step again. Now we've loaded the full 64 bits in output store. This instruction here, STP, is used to store a register pair. Previously, we loaded the register pair X2 and X3 with LDP, so we're actually storing the data pointed to by X2 and X3. You can verify this by looking at X2 and X3 in the register pane, and this time we can see that we have a full 28-bit value stored. So that's how we program our code when we want to use the store instruction. There are also signed variants for load instructions. Examples are shown here. In general, the letter S comes after the LDR part and before the data size designator. A full description of load and store variants can be found in the ARM64 online documentation at the URL shown. This completes part 1 of the ARM64 video series. Part 2 will focus on logic and arithmetic instructions. Floating point is excluded in video 2 and will be included in a later video dedicated to vector and advanced processing. Links to this and other videos are at https://risccomputing.blog. There are 2 freely downloadable PDFs covering RISC-V and ARM64. Together, the documents exceed over 500 pages. The PDFs are supersets of the information contained in the videos.